An alloy is a combination of materials to make a substance that has properties that are different from the original materials. Aluminium by itself is too soft to stand up to the pressures a piston copes with. But if it is mixed with other materials, alloys are produced that are ideal as pistons. In the same way, different steels can be made with a huge range of properties by changing levels of carbon in iron. Alloys can be designed with exactly the properties a particular part needs. The pressure and temperature of a gas are linked. As pressure goes up and down, so does temperature. This container has a fixed amount of gas. A plunger seals one end of the container. A pressure gauge is attached and a thermometer. Pushing in the plunger increases gas pressure. It forces the gas molecules into a smaller space. As a result, they move faster and make more impacts. This causes the gas to heat up. And the overall temperature of the gas rises too. An increase in pressure produces a rise in temperature. Pulling out the plunger reduces gas pressure. It gives the molecules more room to move. They make fewer impacts. The energy level of the molecules falls, and so does the temperature of the gas. A fall in pressure produces a fall in temperature. Now let's see what happens when it is temperature that changes first. When a gas is heated up, its molecules gain energy and start to move more quickly. They make more impacts. This increases the pressure the gas is exerting. Increasing the gas temperature produces increased pressure. Cooling has an opposite effect. The particles lose energy and slow down. They make fewer impacts. Pressure falls. So, for a fixed amount of gas, higher temperatures produce higher pressures, and lower temperatures produce lower pressures. This is put to use in compression ignition or diesel engines. Air in the combustion chamber is highly compressed by the piston. This causes such a large rise in air temperature that when fuel is sprayed into it, the mixture ignites. The cylinder of this bicycle pump contains air. Its exit is sealed with a pressure gauge. As the plunger is pushed in, the air is forced into a smaller volume. At the same time, the pressure gauge shows an increase in pressure. It is this increase in pressure that allows the pump to do its work. When the plunger is pulled out, the volume occupied by the gas grows larger and the pressure drops. Larger volume, smaller pressure. Smaller volume, higher pressure. Pressure and volume are in what is called an inverse relation. As one rises, the other falls. Reciprocating. Reciprocating means going back and forth over the same path. Using reciprocating action to make rotary action has many applications, large and small. The temperature of a gas is a measure of how much energy it has, and the more energy it has, the more work it can do. This is because heating gas particles makes them move faster, and they exert larger and larger pressure on the surfaces of their container. Higher pressure means the particles exert increased force, until eventually they are able to do work. This is especially true for the very high temperatures generated in combustion. The more energy the air-fuel mixture has, the more force it exerts on the piston and the more work the piston can do. That's what happens during the power stroke.
Let's look at the basic principles of 4-stroke and 2-stroke petrol engines. This is a cylinder for a 4-stroke petrol engine. The first step is to get the air-fuel mixture into the chamber. Mixture enters through an inlet port that is opened and closed by an inlet valve. This is called intake. Next is compression. The piston compresses the air-fuel mixture into a smaller volume. A spark across the electrodes of a spark plug ignites it and it burns. This burning is called combustion. The burning gases expand rapidly and push the piston down the cylinder until it reaches bottom dead centre. The reciprocating action of the piston turns into the rotary motion of the crankshaft. The crankshaft forces the piston back up the cylinder, pushing leftover gases out past an exhaust valve. And everything is back where it started, ready to repeat the whole process. The whole process is a cycle. A new mixture enters and is ignited. Combustion occurs, expanding gases drive the piston down and turn the crankshaft, which pushes the piston back up the cylinder. These 5 events occur in all internal combustion engines. How they happen can change, but they are always there. In one 4-stroke cycle, the crankshaft does 2 revolutions. In those 2 revolutions, how many strokes does the piston make? It does 4 strokes. Out of those 4 strokes, how many actually produce energy? In one 4-stroke cycle, only 1 stroke out of 4 delivers new energy to turn the crankshaft. Let's look at the principles of the 2-stroke petrol engine. The 2-stroke petrol engine is different from the 4-stroke petrol engine. In a 2-stroke engine, the inlet and exhaust ports are opened and closed by the movement of the piston. But it is still an internal combustion engine and has the 5 events common to all such engines. Intake occurs when the air-fuel mixture enters the crankcase. It's then transferred from the crankcase to above the piston. Compression, forcing the mixture into a small volume. Ignition, when the spark from the spark plug ignites the mixture and it burns. Power, where energy released by combustion generates the force that turns the crankshaft. And exhaust, removing leftover gases. As in all internal combustion engines, these 5 events must occur, but not always in the same way. The whole process is a cycle. A new mixture enters and is ignited. Combustion occurs. Expanding gases drive the piston down and turn the crankshaft, which pushes the piston back up the cylinder. In one 2-stroke cycle, the crankshaft does 1 revolution. In that 1 revolution, how many strokes does the piston do? 2 strokes. Out of those 2 strokes, how many actually produce power? In a 2-stroke cycle, only 1 stroke delivers energy to the crankshaft. This section looks at major components of the 4-stroke and 2-stroke petrol engine. Because they operate on similar principles, many of their components are similar too. For example, their engine blocks both operate under working conditions of very high pressures and temperatures. And new designs and materials to make them work more efficiently are always being tested. Many vehicles still use cast iron, but some have aluminium alloy blocks. The main gain is a saving in weight. Aluminium alloys can be made as strong as cast iron, but they're lighter. This is also true for cylinder heads. Combustion chambers in the cylinder head come in many different designs. To help hold in the extreme heat and pressure of combustion, a seal is made between the block and cylinder head by a head gasket. The 4-stroke petrol engine has other passages cast into the head to carry oil for lubrication and coolant for cooling. In a 2-stroke petrol engine, lubrication occurs by mixing oil with the petrol, so oil passages are not needed. And if, like many 2-strokes, air cooling is used instead of liquid cooling, there's no need for coolant passages in the cylinder head. Another difference between four-stroke and two-stroke petrol engines is how they deliver air-fuel mixture to the cylinder. In a two-stroke petrol engine, separate passages called ports let air-fuel mixture into the crankcase and cylinder and exhaust gases out. They're covered and uncovered by the piston as it moves up and down the cylinder. In the four-stroke petrol engine, the inlet and exhaust ports are opened and closed by valves. These valves need a system to control how they work. The valve is held in place by a valve guide with a spring on its stem. A rocker arm is attached to a stationary shaft that allows the arm to pivot. The rocker arm compresses and releases the valve spring so that the valve opens and closes. The valves need a system to control how they work. This is done by using cams. A cam is a lobe on a shaft. It's specially shaped to open the valve, hold it open and let it close. The cams control the valve action, but what drives the cams? Cams are attached to a camshaft. In modern vehicles, it's usually mounted over the cylinder head and is called an overhead camshaft. Intake and exhaust lobes can be on the same shaft, or there can be a shaft each for intake and exhaust. Notice that in this design there's no need for rocker arms. It's a much simpler arrangement. A camshaft can also be mounted in the engine block near the crankshaft. As the camshaft rotates, motion is transferred through the pushrod to the rocker arm. It pivots and opens the valve. The camshaft keeps all of the valves working in sequence, but all of this still must always happen at the right time. Air-fuel mixture must enter at the right time in the cycle, and the piston must be in the right place when the exhaust valve opens. The position of the piston is crucial, but what determines that? The crankshaft. It helps to synchronize all this activity. In one cycle of a four-stroke engine, from intake through compression, ignition, power and exhaust, how many times does the crankshaft turn? Twice. It makes 2 revolutions. During that time, what happens to the valves? They open and close once. So the cams must turn through just 1 revolution, as does the camshaft. In each cycle, the crankshaft turns twice and the camshaft only once. So the camshaft must turn at half the speed of the crankshaft. One way to do this is with gears. One of these gears has 40 teeth and the other, the driving gear, has 20. When they mesh, the larger one rotates at half the speed of the smaller. If these gears are separated but linked with a chain, it makes them turn in the same direction, but they still turn at their same speeds. If the smaller gear is on the crankshaft and the other is on the camshaft, how fast does the camshaft turn compared with the crankshaft? Half the speed. Just what the system needs. The position of the ports is important for how mixture enters the cylinder and for how burned gases leave it. Removing exhaust gases is called scavenging. If they aren't fully removed, it reduces engine efficiency. Some engines use a deflector on the piston crown. It directs air-fuel mixture up towards the spark plug and exhaust gases down towards the exhaust port. This reduces the amount of incoming mixture escaping through the exhaust port and helps remove exhaust gases. How scavenging occurs depends on the design of the cylinder and ports. Crossflow scavenging occurs when mixture enters on one side of the cylinder and exhaust gases escape on the other side. No valves are used and mixture flows across the cylinder. Loop scavenging means mixture enters the cylinder across the top of the piston and is caused to flow upwards in a loop before moving in the direction of the exhaust port. In a two-stroke petrol engine, the oil and petrol are usually mixed before they enter the engine. Different engines use different ratios, as given in manufacturer's specifications. Oil, air and petrol enter the crankcase. The high temperatures vaporise the petrol and the oil lubricates the moving parts. A four-stroke petrol engine crankshaft is basically the same as that in a two-stroke. At first, the shape may be a surprise. Why won't a simpler shape do the job? It's all to do with balancing forces. With its weight evenly balanced, this top spins properly. By adding a magnet, it now becomes unbalanced. Without removing this magnet, how can the top be made to spin properly again? Put an identical magnet on the other side. Then the weight is balanced again. The second magnet acts as a counterweight. Counterweights appear in unusual places. They're essential for some systems to work at all. Crankshaft counterweights help keep the rotating components in balance. They help keep the crankshaft turning as smoothly as possible. The crankshaft turns because of the forces transmitted through the connecting rods. At the same time, it must be held in place. That's done by bearings. They reduce friction and allow free movement. The crankshaft is held in place in the engine block by main bearings at points called journals. Different bearings do different jobs. These bearings support the crankshaft in place but let it turn freely. The crankshaft also needs to be located to stop lateral movement. This is done by using flanges. Between the connecting rod and the crankshaft are connecting rod bearings. They protect the spinning crankshaft at points also called journals. On the rear of the crankshaft is a heavy flywheel. It stores up energy from the power stroke and helps keep the crankshaft turning. In a four-stroke engine, only one of the four strokes in a cycle delivers power. In one cycle, the crankshaft makes 2 revolutions. In a two-stroke, every second stroke is a power stroke. Without the flywheel to store energy from the power stroke, the crankshaft will slow down and stop. Let's look at the four-stroke and two-stroke petrol engine cycle. What is a stroke? It's the movement of the piston from top dead centre to bottom dead centre. Calling an engine four-stroke means its engine cycle has 4 strokes. A four-stroke petrol engine uses internal combustion, so those 4 strokes must include the 5 key events common to all internal combustion engines: intake, compression, ignition, power and exhaust. Let's look at a simplified model. The intake stroke starts with the exhaust valve closed, the inlet valve opening and the piston at its highest point, top dead centre. It starts to move down, increasing the volume above the top of the piston. This makes pressure inside the cylinder lower than pressure outside. This higher outside air pressure forces air-fuel mixture into the cylinder. The piston reaches bottom dead centre, the inlet valve closes and the intake stroke ends. Both valves stay closed as the piston leaves bottom dead centre. The piston moves up, squeezing the air-fuel mixture into a smaller and smaller volume, which compresses it. That makes its temperature rise, and that makes combustion easier. Just before the piston reaches top dead centre, the next key event occurs: ignition. Burning, expanding gas generates the force to push down the piston. This is the power stroke that drives the engine. The piston now moves from bottom dead centre to top dead centre. The exhaust valve opens and the piston pushes out the leftover gases. Let's look at the cycle operating. Intake takes in air-fuel mixture. Compression squeezes the air-fuel mixture into a smaller and smaller volume. Ignition The mixture under pressure is burned. Power. Burning expanding gases push the piston down, creating a power stroke that turns the crankshaft. Exhaust. The piston moves upward, forcing burned gases from the chamber. All 5 events occur in this order in each of the engine cylinders. Let's look at the cycle of the 2-stroke petrol engine. Calling an engine 2-stroke means its engine cycle has 2 strokes. As in a 4-stroke engine, a stroke is the distance from top dead centre to bottom dead centre. The piston moves up the cylinder from its lowest point, bottom dead centre, compressing air-fuel mixture already in the combustion chamber. As it rises, the top of the piston covers the exhaust port and the transfer port. This is a 3rd port or passage between crankcase and cylinder. The bottom of the piston uncovers the inlet port. At the same time, the rising piston is increasing the volume of the crankcase below the piston. Pressure in there falls until it's less than outside air pressure. This pressure difference forces more mixture into the crankcase. As the piston reaches top dead centre, mixture already there ignites, and expansion of gases starts to drive the piston downward. The piston moves down. The bottom of the piston covers the inlet port as the top of the piston uncovers the exhaust port. Opening the exhaust port starts the scavenging process. It releases the pressure above the piston and burned gases escape. At the same time, closing the inlet port means the descending piston is compressing the air-fuel mixture in the crankcase. The top of the piston uncovers the transfer port. Increased pressure in the crankcase forces fresh air-fuel mixture up through the transfer port into the cylinder, replacing the burned gases, and the cycle starts again. This intake system is called a piston port system, because the piston acts as a valve to cover and uncover the ports. This intake system uses a rotary valve. The crankcase has a hole open to the crankcase chamber and a rotary valve cover attached to the carburetor. The rotary valve is mounted on the crankshaft, between the crankcase and the valve cover. As the crankshaft turns, the rotary valve rotates with it, opening and closing the inlet port as it does so. Some 2-stroke engines, such as outboard motors, use an intake system with a reed valve. It's a small, flexible metal plate that covers the inlet port, and it can be attached to the crankcase or to the inlet port. It opens and closes automatically, according to changes in pressure in the crankcase. The 2-stroke engine makes only 2 strokes, 1 up and 1 down for each time it fires. That's only 1 revolution of the crankshaft for each cycle. Compare this with a 4-stroke that needs 2 revolutions of the crankshaft for each engine cycle, and only 1 power stroke for each 4 engine strokes. Let's run the cycle again. The piston moves up the cylinder. The top of the piston covers the exhaust port, the bottom uncovers the inlet port. Air-fuel mixture enters and circulates in the sealed crankcase below the piston. The piston rises and compresses the mixture above it. A spark plug ignites it and it burns. Pressure from the expanding gases pushes the piston down in a power stroke. The top of the piston uncovers the exhaust port and lets exhaust gases escape. The bottom of the piston covers the inlet port and forces air-fuel mixture up into the now open transfer port. The piston reaches bottom dead centre and the crankshaft forces it back up to repeat the process. Notice which events occur above the piston. Compression of the air-fuel mixture into the combustion chamber, combustion for the power stroke, and scavenging of the exhaust gases. Notice the events that occur below the piston. Intake into the crankcase, pre-compression of the air-fuel mixture in the crankcase, and the transfer of mixture from the crankcase through the transfer port and into the combustion chamber.